मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, my dear students, this is 30 in the series of mechanics of metal forming. In 32nd lecture we started the finite element modeling technique for metal forming. So, we would, if you recall back the previous lecture, we started the basic concept of finite element method. So, let us continue with the same, and as I told, the whole basic concept of finite element method is, if I say in 3 steps, it is the pre-processing, then solver and the post-processing. Pre-processing, where we take the domain of the interest, this case it is metal forming, maybe any process. So, this domain is discretized. We break the whole domain into small elements and nodes, that is called as discretization, and then we choose the proper type of element, the interpolation function between the nodes, and many other issues as discussed last time. And then once the whole pre-processing, that means discretization, choosing of a proper element and all those things are done, then we can go ahead for the solving of the problem. So, solving also, as I told you tomorrow, 3 major process where we solving 3 different direct approach, and then Galerkin approach and all those things we discussed. So, let us start with that same, and if you recall, we concerned with solving the basic equations, as I last time, if you recall the equation where there was over a given volume of the domain, the surface, that the T bar, if you look at this integral equation, where the one equation one can find it out for every choice of delta V x. So, that is, if you look at this equation, over the surface and then plus over the volume, that equals whole volume, the integral over whole volume, sigma x bar, delta epsilon and dV. So, but you know that the u bar x, which is infinitesimally many values has got. So, equation cannot be solved if it is so. So, for getting the answer for u bar x, that is the field variable, one has to find with a safe function, as I told you, n x. So, that is u bar x. For finding the answer, the values of the field variables, so one has to sum up all the elements, the values, all nodes, nodal values, and therefore we propose a safe function for solving the equations. So, if you use the same safe function for delta V bar x as well, in that case what will happen, which is given here, delta V bar x would be equal to the summation for the n elements delta V n, capital N n x bar. So, n n is actually safe function, the type of shape function you choose. Actually the choice of shape function nn, it depends on how do you divide the region into elements, and how do you choose a proper polynomial nn, capital Nn. So that is the deciding about the region of the element. How do you break the whole element region into elements, and the selecting of a proper polynomial capital Nn. So if you look at this figure, how the elements are divided here. See, it is all triangular element, then further smaller element, and then there one can go for the quadrilateral element, like that. So what happens, the shape function is such that capital Nn, when you choose capital Nn, that is the shape function polynomial for the shape function capital Nn. This thing should be kept in mind that capital Nn is 1 at all the node values, at all the nodes. If there are n nodes, then at all nodes, n number of nodes, the capital Nn must be 1, and when if suppose m is the number of elements and n is the capital number of nodes, if suppose any problem. So capital Nn must be 1 at all the nodes, and it should be 0 everywhere where nodes m and n are not equal. At those nodes where m and n are not equal, everywhere it should be 0. So capital N shape function will yield n equations with n unknowns, right. This point has to be noted very carefully. So that means if you look at this figure, 5 different figures which is possibility of dividing the whole region, if you look at, so that means n shape function will yield how many equations? N, capital N equations, and where you can get n unknown values. So that means you can now get the basic equation for nodal variables. So what becomes the basic equation for nodal variables? This is given here. So the basic equation for nodal variables becomes, that is the integral over the surface T bar delta V bar ds plus integral over the volume F bar delta V bar and dV, and these two summation must be equal to over the whole volume of interest sigma multiplied by delta epsilon dV, and that is nothing but the function capital F bar u bar multiplied by delta V bar, and that is equal to capital R bar delta V bar, where capital F bar u bar is equal to capital R. So that means it is now true that the internal forces are equal to external forces, right. So suppose the problem is a linear problem, right. If it is a linear problem, then that means capital F is almost representing capital U. That means for the linear problem, capital K multiplied by U, if it is suppose displacement, U bar is displacement, so that must be equal to force, right. So that force which I said as F bar U, that would be equal to R bar, because earlier I represented it as R bar, and where K is taken as the stiffness matrix. So this is for one element, please remember. We are considering the basic equation for one nodal variables. So that is K U bar is equal to R bar, and where K is the stiffness matrix, right. So this is what the basic. So if I summarize the FEM method, what we have done so far, that first you discretize the partial differential equation. The partial differential equation represents the physics of a problem, Like if it is metal forming, so the constitutive equations of metal forming, right. If it is heat flow problem, so constitutive equations of heat flow problem. If it is fluid flow problem, then the constitutive equations of fluid flow problems. So likewise, so first thing is that you discretize the partial differential equation, then use principle of virtual work, right. Then divide the solution region into simply shaped element, very simple element one must take, not very complicated elements, and then make the simple polynomial that has to represent the elements, right. And then partial differential equations become matrix form, then this partial differential equation is converted into a matrix form which is soluble, and which is one can assemble over the matrices, and then one can solve it for the whole unknown variables, nodal unknown variables. So as I told you, the choosing a proper element is very important for getting an accurate result for any finite element solution. So choosing the right element, that also depends on the safe function capital NN, right. That means, as I told you, the field variable u bar x bar, x is the direction where the variation occurs. So that is equal to the summation over n elements u bar n capital N n x bar. So that is the safe function. So number 1, for every node n of an element, there is a safe function which is capital N n x bar. One has to remember this. So for every node n of an element, there is a safe function capital N n x bar, that is 1 at this node and 0 at all other nodes. That is what is the definition of safe function. Secondly, the safe function is the polynomial of lowest order with property which is there in 1, just mentioned, that is it is 1 at this particular node of the interest and it is 0 everywhere, right. So these 2 points has to satisfy with any safe function. One can go for a linear safe function, one can go for quadratic safe function, one can go for other safe function. Suppose one takes a 1D problem. So look at this figure. For 1D problem, this is the case. So you have element 1, element 2 and element 3. So because it is 1D, so one can see here that there are 3 elements now. So there are 4 nodes here. The round blackened part represents node and in between line represents element. So element 1, element 2 and element 3 are there in this figure within these 4 nodes. And now you see, if one chooses the linear safe function, so that is how the linear safe function has been said. That means if you take the element number 1 and node 1, so node 1 the value is 1 and the node 2 it is value is 0, right. If you take the element number 2, the value is 1 and all other it is 0, right. So one can see here. So this is the left side which is given for the linear element. If you take a quadratic element on the other side on the figure, the element 1 and element 2 only, if you choose, the quadratic safe function has been shown. You can see, right. So this is how the it is very important to choose a right element. the right, I must say the right element. If you hang over, otherwise you will hang over, the result will not come correct. So, these are some of the issues. This was for one dimension, and if it happens for a multi-dimensional element, then the same function of a 4 node element which is bilinear can be like this here. So, shape function of a 4 nodal element that is a bilinear, that is the case where the multi-dimensional elements can have. So, this figure shows the shape function for a 4 node element which is a bilinear, one can see, that is the 3 directions now. On the other hand, if you look at this figure, the shape which is shown it for shape function of a 9 node element which is bi-quadratic. You can see the variation of the shape function. And the last one shows the shape function of a 8 node element which is bi-quadratic. So, you can see here. Now, you look at the variation, how it is varying. So, this is the case, these 3 different cases for multi-dimensional element. So, it is very important to choose the right element. Then the second thing is that one has to choose the element properties. For an example, the element properties means if I ask what is the strain. So, the strain the epsilon is equal to deva u bar by deva x bar, and if the property of the element is elastic property, then one has to be equation corresponding, that is the stress is equal to E multiplied by epsilon. So, if I choose the first order element, that is a linear element, right. So, that means the u bar must be linear, the variation of u bar must be linear, and in that case strain would be constant and stress would also be constant, alright, but u bar must be a linear for the first order element. If you take the second order element, so u bar must be quadratic to represent the second order element, and therefore what would happen to the strain, if it is second order element where the u bar is a quadratic, so the strain must be linear and stress must also be linear, and that is how use higher order for problems with a smooth solution. So, elliptic partial differential equations like, right. So, you always one has to use a higher order for problems where the smooth solutions are expected. As far as the solving integration problem comes into, as I told, the nodes and integration points when you solve the problem integrals. So, usually one has to solve this integral concerned in the formulation here or any finite element problem, you have to solve it numerically. Generally it is solved numerically. So, here is the figure which shows the integration point. Suppose this is the integral and the integral points are shown around x, and the function, corresponding function f(x) is shown around the y axis. So, if you solve it numerically, that means that is the integral sigma delta epsilon. So, suppose this is the integral. So, as I told, it is the summation. So, this integral is nothing but the summation over p, that is the point, integration point, and sigma p epsilon delta epsilon p Vp, that Vp is the volume of the interest. So, generally proper integration point is used, and whether it is a stresses, a strain, etc. at integral point. So, one can see here. So, that is the integral point, and that represents the summation of so different ways of choosing integration points are possible. However, one can go for full integration where nth IPs with n nodes on edges are there. That means n number of integral points are with n nodes on the edges. One can, that is called, we can say as the full integration. One can go also for the second case where the reduced integration are done. So for in the reduced integration there is 1 minus 1 integration point with n nodes on the edges are selected, are taken. So there are many ways to do this. So if it is seen in nutshell, what is the rule of thumb for choosing element out of this discussion? So the rule of thumb for choosing elements is that choosing the wrong element type is one of the most common mistake in finite element simulation. If you choose a wrong element, that's a great mistake. So there are certain rule of choices for choosing a proper element. So these is listed here. So number one is that if the problem is elastic problem, so choose second order element, right? And in that case one has to go for reduced integration method for solving the integral. So that means if the problem is elastic, choose second order using reduced integration points. Secondly, never use fully integrated first order element in bending problems. This is another suggestion. If problem involves contact and does not converge, so use first order element, right? If the problem contains stress strain discontinuities, that is plasticity, the first order may be better. Then if elements deform very heavily, and in that case first order may be a better choice. And avoid first order triangular or tetrahedron elements. And if the material is incompressible, so one has to use hybrid elements that may also be better in plasticity problems. And look out for Horst glassing with first order reduced integration element. So and if following these rules, even if there is any problem, then one can consult the program and manuals for available type of element that is available, and whatever guidelines are there, one can consult their own program and manuals. So but however, these are the some of the thumb rules as I said. So based on these, one has to then create a mesh. So creating a mesh, there are certain strict rules. That means there should not be free nodes. Nowhere when you create mesh, there should not be any free nodes. Like here this figure, there is a free node here. So don't mix up shape function of different order also. You choose a uniform shape function. Like this on the right side, this figure shows a mesh. So for designing mesh, there are certain rules. So if it looks like good, it is good. That's a very common sense. But prefer quadrilaterals to triangular elements, and use regularly shaped elements, right? Then large gradient require high density, so that has to be taken care. And smooth size transitions must be used. So, if you follow these basic rules, you may hang up a easy path for creating mesh. There are many meshing algorithms available, but like structured mesh, then triangular mesh, then mix 3 by 3 to 4 nodes, that is the mixed one, triangular as well as quadrilateral are structured. And then there are also situations when there is a mixed 3-4 nodes and local local refinement also. So this figure shows the different algorithms one can choose. So the user's choice is very important. If you start with the proper element, then proper meshing algorithm, you hang up and you have the smooth way to get the solution. So this shows the 4 different structures, meshing algorithms: structured, triangular mesh, mixed 3-4 elements, and mixed 3-4 elements with local refinement. So one can see here the structured is very uniform. Even the triangular mesh is quite useful, and mixed one is there, and then sometimes the mix with local refinement is also preferred. And so looking into this, there are advantages, certain advantages and disadvantages of finite element method or analysis when you design, and especially in early stage of the design process. Whenever you design, usually what happens, designing a geometry is different, but designing the geometry according to the load requirement and the problem or the constraint is another issue. So there are certain advantages and disadvantages. In order to decrease development times in designing, it is necessary to apply finite element method analysis even in very first step of a design process. So this first finite element method analysis should be done by the designer himself. Without any doubt, it serves the opportunity for a significant speed up the design process. However, some problems have to be taken into account, like you have a CAD data. If you look at this figure, basically you have a CAD data, and then you have a FEM preprocessor, and then you have, suppose you have a FEM solver. So you will find that if you take this order, CAD data, FEM processor and solver, then there is a topically decreased in this order. So that's the initially the CAD data is hot, then the FEM processors, and then the solver has to be pointed at the end. So that's the decreasing topically. And however, there is an increased disconnections, right? So this is what shows the data flow between CAD and FEM, right? So the disconnection is more at the inside of the solver, and it is minimum at the data CAD of, but as a topicality is concerned, it is maximum at the data side and it is minimum at the solver side. So actually the simulation, any simulation has improved drastically, and it depends on the knowledge, it depends on the practices, and it also the complexity of the problem. Basically, computer design system developers designed a finite element method menu structured, especially tailored to be used by a designer. The main goal has been easy handling for solving the structure standard problems. Thus, any designer can apply simplified finite element method tools today, and only very little training is recommended for proper use of these tools. So, handling of complicated problem when it comes, and when it is however it is excluded for complicated situation, it is still has to be done very specialized manner. So, this figure shows the change in the complexity of soluble finite element problems and personal knowledge which is required on that. So, if you look at that, before 20 years where the knowledge was very less and complexity was not that much. So, now as you move today, the knowledge is used and therefore the complexity is reduced. So, earlier because the knowledge was less, the very complex problem was not possible to solve. But once our knowledge in finite element method is increases, one can solve very complex problem, any metal forming problem. And you will surprised to know that in today's industry where we talk of a finite element formulations for all kind of metal forming, including thermal, including hybrid problems, right. So, as far as the people concerned in design groups are concerned, the finite element method calculations in the design area require changes in the staff management as well. A sound FEM calculation requires appropriate training. One can have only few commands of a very simple menu in finite element tool for designers. There are so many softwares now available based on the tools, basic tools of finite element method, and thus the training are very short, but usually much too short, and knowledge about the functions of the commands only is insufficient, as it should be. It shows here in this data. Say for example, the reasons for incorrect finite element calculation by a designer has been the chances which could be, that is, if the wrong application of the load, if the load is not applied, that's the, then the estimate would be only 20% you will get the result if it is a wrong load. If there is a wrong application of the restrains, so the chances is that you get 30% only estimate. If there is a wrong free cutting of the model, if you do not take the proper reason for considering the finite elements solution out of a big problem, so there may be, if it is chosen wrongly, then there is 40% estimate would appear. And if there is a wrong handling of the finite element program itself, so there is a 10% possibility only that there. So obviously about 90% of all incorrect calculations rely on missing basic knowledge in technical mechanics. In consequence, only designers familiar with basics in technical mechanics should do finite element calculation. Therefore, it is therefore expected that one who knows the technical mechanics of finite method, they must only solve. And if people do not know, then it is better not to try for the solution. Regarding the results of finite element calculation, the missing knowledge of finite element method uh, basics easily results in enormous interpretation of these results too. So, even if designer never might look at junctions and elements face to face, they importantly need well founded knowledge of the background. Therefore, a conception for a training which has been successfully applied to around many more than 300 designers, and so usually that requires that if it is 3-day program, then for the first day one has to refresh the basic and tasks, the exercises in technical mechanics, basics in finite element method and finite element theory, the first day, suppose if it is 3-day program for finite element method. Second day, then one should handle the problem. So that means the task exercises to any function with practical backgrounds. Then third day, workshop with present problems, and models of the designer must be taken up. So it has proved usefully to add an additionally 1-day workshop therefore on 1 week after the training. One can deal with the questions therefore arising from the specific work of the company, and that's how one can improve upon to solve the problems using proper finite element training. Usually companies most of the companies are already equipped with finite element calculation, and along with their groups, and they usually install finite element calculations into design process. This is what's the usual practice in industries. So beside the objective of any recognition of the weak point in the design model, the finite element calculation group, whatever it is, should be released from the daily routine work by this, if one is going for the finite element. However, it will not work without specific supporting the designer by finite element method calculation specialists, as this is what is, say, a designer is separate, the finite element specialist is separate. One has to be very quickly, so the finite element specialist has an objective, and that he has to work on a particular CAD designer. So you look at this is the one figure where the distribution of tasks and responsibilities between designer and FEM specialist has been shown here. Okay. So at the left side, the FEM specialist knows the objectives. So whatever he receives a CAD model or design, then after proper discretization, and then he will apply the choosing the proper element and then solve it. And therefore the FEM specialists support the CAD designer. So if there is something wrong, the load, because a proper improper model, there is something excess load. So the FEM specialist, after running the solver over the given design, can tell him that let us choose and change this shape from previous one to this one, and then again try with the FEM solution, and try the field variable calculation and then check whether it is now okay. So, a designer should never calculate with the highest possible accuracy, right, but hopefully only with sufficient accuracy has to. He needs objective for values of loads, stiffness and other goals for his optimized design. At this point, the finite element method specialist must that means convert complicated load cases to quasi static load which is applicable by the designer. So, that is how the things will improve. And thirdly, if one sees the consequences for the organization, for any organization of finite element method calculation in a design process, because design process is what is the very important one, and therefore it will also affect the process of design. To achieve the goal of intense time saving priorities and time schedule have to be set. When there is a situation where you have to give the solution very quickly, but while arguing about the invest in hard and software like of then the qualification of a personnel must be has also to be seen, and where it must be sure that this changes is going to give something. But if this important last section is ignored or neglected, one can be sure that any investment in the computers and personal a proper specialist of a firm will go in vain. So, the resulting therefore will be only disappointing to the co-workers and to the others also. So, the present effort in time and money, it matters. Then when one uses the finite element methods and in a bulk in the problem solving, then there are one has also to see the achievable savings and the effort for the future and related investment, and then only one can go for the new efforts and then proper. So, finite element application today whatever has been established, it is going to give you lot of saving. So, in fact, it is often missed that installation of finite element method into design process result in increased work to be done by a designer. It is not like, in principle this should be no problem for weak points in models, will be recognized and removed in an early stage. Therefore, this investment in time and money usually will be saved in later stages of the project. Therefore, however, the large company depends on the company, how large it is, and the other division the harder the realization of this change in the time management, if it is there any. So, it come to pass that the time schedule for designer may be shortened for installation of finite element method into design process. Therefore, it should save time. In fact, as a rule of thumb, a reinvestment of about 1/3 of the saving in time and money is necessary. Suppose if there is a 100-day of experiment should be saved, if 100 days of experiment should be saved, and investment therefore of around 30 days in simulation is required. So that is how the order. In fact, one will save only 70 days in this case. The same relation of saving to reinvest is effective if any FEM calculation are in the group should be therefore relieved. About 1/3 of the time saved has to be reinvested in support of the designer to enable them to achieve the this relief of the fact, right. So this is what's the importance to variety of important decision in an early stage of the project is shown here. Another figure where the ratio of presently accumulated costs to the cost which is generated at the moment of while running the project is shown here. So this is what shows the generated cost, and this is what the accumulated cost. So the run of the ratio of the actual accumulated cost to the cost which is generated at this time, if you look at here, for the future was investigated, and this has been shown here for run time of a typical project. So one can see that this study shows that more than 80% of the costs are generated in the first stage of the project, where only little costs accumulate. These important results are well known since about 20 years. However, it took until the recent year to start a process of many other implementation of effective tools for simulation into the groups, various groups of the those are responsible for development and design. But without change in the project and time management, the success becomes dangerous. The fourth thing one has to see that the possible versus sufficient accuracy of the finite element solution in the design process, as I told. One argument sometimes comes, especially FEM side, FEM specialist side, against implementation of finite element method into design process. Is the lack of accuracy of the calculation. Sure, a designer generally will conduct calculation with large errors for the work with the specified problem, but is this reality? Is this really an argument against finite element method in design? No, accuracy is no end in itself, not seldom. Meaningful work like island or ivory tower are uttered in companies while taking and discussing or talking about the FEM simulation and calculation over the groups. So in order to objectify this discussion as far as whether when it has to be used during the design process, which become rather emotional, the result of investigation of an other people like economists and many other things, studies was carried out, and this can be, it is shown here, that is we call it as the Pareto chart here. So, this shows result about 80% of a goal are reached with 20% of the effort needed to reach 100% of the goal. So, one can see here the goal has been here, the effort is now 100%. So, that is the one by one way understanding between the designer, between the CAD modeler, and then running it, then changing. So, this process may cause sometimes misunderstanding, but this data shows that about 80% of a goal are reached within 20% of the effort needed to reach 100% of the total goal. So, usually this is what is the a basic discussion. Application of Pareto principle to the accuracy of finite element application calculations in the design. If one sees, that means if you apply the Pareto principle, so the calculation will speed up by a factor of around 5 if an accuracy of 80% is sufficient. Even in the very first step of design process, accuracy is not needed, just the feasibility of the idea has to be checked initially, and approach of any goal with a say butter of 20% should be sufficient and effective. Self evident, not every calculation must be carried out by designer if high requirements are met. No buffer can be defined and high accuracy is needed. These calculations in fact belong to well trained specialists therefore. So, the specialist becomes, FEM specialists become much important here. Inquiries at several companies, it shows that a buffer of around 20% is sufficient for practical work. Most experiment shows much higher variation. Now, the time where any calculation which was computed as exactly as even possible come to an end therefore. Now, today designer and calculators must answer the question of the ratio between economic viability and accuracy of the calculation. So, these has to answer. So, this discussion I especially took to see that this concept, because at all when we apply the when we are going to model finite element method to various metal forming problems, how the designer specialization and the understanding with the CAD modeler, it becomes importance. So, the process is tedious, but the accuracy, investment on software and hardware as far as concerned, today most of the companies are following FEM, but it's and they are getting benefited. So, this is what about the today's discussion. The basic, so far we have discussed the basics of FEM. Now, from the next in next lecture we would cover, we would take 1D problem and 2D problem. Now, let us these methods let us apply, and let us start with a very simple situations, cases we would discuss tomorrow, and hopefully you will come prepared in the next lecture, and so that let us see how it can be useful for. But these discussion at the inside which we cover today, this is just for the sake of applicability of finite element to the designer and then how these are related. and especially at the industrial approach one has to, and where the cost is seen. Anything in the industry is looked in terms of return. So that's how I discuss a little bit here. So I once again thank you all for keeping so much patience, and please give your suggestions, give your feedback over the net, and so that if you can make further better for you. So thank you very much.